Okay, أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. This is yet another video tutorial, and this time I am very quickly going to go over the our mini test 1, which we did yesterday. So quickly, as I said, I'm going to go through this. Some of you did very well, so we do not really need to go through much of the detail, but for the benefit of those of everyone, we'll do that. So the first question is, everybody read that. So the first question is really saying that if you have these three charges are placed on the corners of or three corners, and one of these guys is minus q, he wants two of them are positive and one of them is negative, and they have the same magnitude. So he wants to know the direction of the electrostatic force on the charge at the lower corner. He just wants the direction, that's all. Okay, so I just prepared this. Okay, let me just make sure that it is, yeah. So the distance is the same. So that means since this is positive and this is positive, so this force, the first force, let me call it F1 this way, that's Q1, and that's Q2. And the force on this one, and this one is repulsive force, so it will be this way. And if this is 2, then the FQ2 will be this way. It's the same magnitude, same vector magnitude. And so the direction of the force will be the resultant of these two vectors, which can be drawn as very easily using the head and tail method. It can be drawn as, okay, this one and then plus this one, and that will be your resultant. So the direction of the force will be this way. That's your resultant force. This is the direction that I'm asking for. Okay, that's the first, the answer to the first question. Question number 2. He's asking you to, this is question number 2. So he's asking you to, you just wanted to choose the proper answer, and you have two protons are placed near each other, initially held at fixed. If they are released from rest, what will they do? Okay, so if you have, again, I prepared this. So if you have these two protons, they are held, initially they're held fixed. And once you let go of them, then you know there will be a force that is exerted by these guys, repulsive force, and then we'll go this way. Now remember, I have an F and an F on each one of these guys. One of them, so this guy, the force of this proton and this proton will be this way, and the force of this proton and this proton this way. So, and it will be F12, it will be minus F21. So what does that mean? If they initially start from rest, then since F is not equal to 0, so they will accelerate away from each other. Accelerate means they will start at 0 speed, and then their speed will continue to increase as they get as they move away until the force dies down at infinity. Okay, so that's question number 2. Question number 3. Question number 3 says that you have a dipole. And this dipole is actually placed in an electric field, and he wants you to. He gave you some information or some of the data, the Q's and the distance between them, and the angle between the field and the direction of the dipole. And he wants you to know: is it going to move, and which way is it going to move? Will it rotate, and all of that business? Okay, all of these questions that we're used to now. Let me just explain this, because I know some of you asked me some questions about this. So remember, this is the direction of the electric field. So the electric field is this way. Now we know for a negative charge, the force is defined as F is equal to QE. That's what the force is equal to. Now, if for a negative charge, the force will be not along the direction of the field, but will be opposite to the direction of the field. So let's call this F negative. It will be directed there. For this one, it will be along the direction of the field, and it will be this way. So this will be F positive. Now, what does this mean? That means the dipole will rotate this way. So the motion, it will move, and it will rotate counterclockwise. So that's the answer to the first part of the question, is that the dipole will move, and its motion is the type of motion is rotational motion, not translational motion. It will not translate across the field, but it will only rotate, and it will rotate counterclockwise. That's the answer to the first question. The second question, he wants to find, he gave you some numbers, and he said find the magnitude of the charges and the torque. So since he gave me P, right, and he gave me D, P is equal to Q multiplied by D. d is the distance between the separation between the charges, which is given to me. It's equal to 1.2 times 10 to the power of minus 3. That means it's millimeters. And so that's d. And P is given also. P is 1.4 times 10 to the minus 12. So from there I can find Q is simply equal to P divided by D. Okay, that's the first question. And then he wants you to find the torque. Remember what he said the total torque is equal to? Torque is equal to F D sine the angle theta. Okay, F is given, okay, which is simply Q times, F is given. It's Q times D. And D is the distance between them, Q times E, and D is the distance between them, and sine theta is the angle, this sine of the angle here. Now, we know that we took this as F is equal to QE, and then we have PE sine theta, which is the same thing. So whether you do PE sine theta or or FD sine theta, it's the same thing. All right? Okay, so that's the answer to this, the third question. Okay, the answer to the fourth question, this is a little bit long. Okay, so what do we have here? We have 3 fixed charges. They each have some charge. One of them is positive, 2 of them is positive, and 1 of them is negative. And they're placed on a rectangle of sides 6 and 8. He wants you to find the net electric field at point P. Okay, I prepared the this. Okay, so this is my Q1, which is positive. This is my Q2, which is positive. And this is Q3, which is negative. Let me highlight that just so that you... Okay, so this is negative. Now, all right, so if I wanted to find the net electric field at this point here. So at this point here, P, I want to find E. Now, I know that E, the net electric field as a vector, okay, E net as a vector, it will be E due to charge 1 plus E due to charge 2 plus E due to charge 3. And all of these are, they have to be added as vectors. So that means I have to find the vector, the electric field due to this charge as in vector format, and the electric field due to this charge in vector format, and electric field in this due to this charge in vector format. So for E1 will be, remember how I find the electric field. I go and place a Q positive charge, a test charge there. So this is positive, I'm positive, that means the E1 will be this way. E1 will be along the I hat direction. And 3, this is positive, this is negative, so 3 will be along the minus j hat. So E3 will be along negative j hat. Now this guy, positive and positive, it will be this way, right? And the angle theta, it will be the same as this angle here, right? Same as this angle here, theta, which I can find the cosine and sine and all of that. So this will be E2. Now, so this, what does this mean? This means that E1, I don't need to resolve it because it's already along I hat. And E3, I do not have to resolve it because it's already along minus j hat. So the only one that I need to resolve is this one. Okay. So let me do that very quickly for you. I grab a piece of paper here. Okay, so I need to resolve. First of all, I need to find the magnitude of E1, E3. So E1, the magnitude, is equal to K Q1 divided by the distance square, R1 square, which is K. Q1 is given. R1, is 6. So K Q1 divided by 6 square. Remember, these are in meters. So that's the magnitude of the electric field 1, and it is along I hat. Okay. So I can write the electric field as a vector, E1 as a vector is K Q1 divided by 36, and it's along the I hat. That's my first E1, the first field. The third field, again, is easy. So E3 will be equal to K Q3 divided by the distance, which is 8 square, which is 64, and it's minus j hat. So it's along the direction of minus j hat. So I got my, these are my 2 vectors. As I said, the only vector that is, you may say it's a little bit challenging is E2. E2 is, okay, this way I need EX, which is going to be added, or E3X, which is going to be added to this one, and E3y, which is going to be subtracted from this one, okay, because this one is down and this one up, and this is my theta. Okay, let's first of all find E3, the magnitude of E3. E3, the magnitude is equal to Q3 divided by the distance, this distance here, this distance square. What is this distance here? It's 6 squared, which is 36, plus 8 square, which is 64. So this is the square root of 100. So this is 10. And when I square it, it is 100. Okay, 100. And then I have to find the cosine. I have to find EX and EY for that one. That means the cosine of the angle theta and the sine of the angle theta. Okay, so that means E3x is equal to this number here, KQ3 divided by 100 cosine theta. And remember cosine theta, this is theta, this is 10, this is this guy is 8, and this guy is 6. So cosine theta is really cosine of this angle, which is 6 over 10. So cosine theta is 6 over 10, and E3y is equal to KQ3 over 100 sine theta, which is 8 over 10, and then this will be, as I said, will be added with the to E1, and this will be subtracted from E3, and then you can find the EX's and EY. So this EX total will be equal to where am I? KQ1 divided by 36 plus KQ3 divided by 100 multiplied by 6 over 10. This is all I had. Okay, that's the EX net. And EXY net, EY net, it will be equal to my E3y, which is a positive, KQ3 over 100, 8 over 10, minus my E3, which is the first one, which is KQ, this is Q2, sorry, this is Q2, it's Q3 divided by 64, and this is along the J head. Did I say here Q? Yeah, this is Q2, sorry, this is Q2, Q2, so EX is, this is E3y, that's right, and this is this is from the first, this is Q2. All of these guys are Q2, because the one at this corner is the Q2. So fix that, and then that's your answer for EX, okay, and EY, and that's it, okay. So that's the answer to this question. I may have mixed up the charges Q1, Q3, Q2, Q3, but I'm sure you can sort that out when you're doing this at home. Okay, now the next question, which is the parallel plate capacitor question. So what does this say? It says that you have a parallel plate capacitor, except this time it's not really a parallel plate capacitor as we defined it in class, because both charges are positive. Both sheets are positive, they have a positive charge, which means that if you remember, and we did this in class very well, we did that if these two guys are both positive, so that means if I calculate the electric field here, the electric field due to this guy will be this way, and the electric field due to this guy will be this way, since the magnitude is the same, so the electric field net inside is equal to 0. Now outside, I have this is, remember, this is positive, positive and positive will be this way, and positive will be this way. So the electric field at any point in this side near the sheets will be E net will be equal to sigma over 2 epsilon plus sigma over 2 epsilon naught, which is sigma over epsilon, and as a vector E will be equal to sigma over epsilon and along the I hat, which is this is the I hat direction. Okay, now the second question, so this is the electric field, and then he told you if an electron is placed at point P, what will its acceleration be, magnitude and direction? So if I place a negative charge here, so a negative charge here, Now, obviously, this negative charge will go this way. So that means what? Means that F is equal to Q multiplied by E, and it's minus E divided multiplied by E is the charge of electron multiplied by E. So the force is this way. So this is the force is this way. If the force is this way, the acceleration must be this way. Okay. If the acceleration is this way, so the answer, the acceleration will be equal to. Let me just again grab another piece of paper. Okay, so remember F is equal to Q multiplied by E is equal to Q, the charge of the electron, the charge of the electron multiplied by E, which is sigma over epsilon. Okay, and then F is equal to MA, so this is E sigma over epsilon is equal to M of the electron multiplied by A. So my A will be sigma, the charge of electron sigma divided by epsilon, and then epsilon naught on the charge of electron. So that's the mass of the electron. So it will be this direction, and remember it will be opposite to the electric field. So you either say opposite to the electric field, or you just say towards the positive plate. Both answers are correct. Okay, so that's the answer to the that question. The next question is this guy here. Where does it say? It says that you have two charges, both positive, and they are one of them is fixed, and initially they're separated by some distance, which is equal to 4.2 centimeters away. How close can they get to each other if you let one of them you keep one of them at rest and the other one moves toward it? Okay. Now you know this is an initial situation and a final situation. So this is again what I have drawn here. So this is my one of my positive charges, and this is the second one. This is the fixed one. So this guy is fixed. Okay, and I'm going to allow this one to move this way. Okay, initially with a speed that is equal to 66 meters per second, and then it will move up to some point here x, and at this point x it will stop. And this, so V final would be equal to 0. Now I know, or you know that we're going to do the potential, the total energy before is equal to the total energy after. So energy before and I is equal to total energy at the final position for this one, for the moving charge, because this is the moving charge and this is the fixed charge. Okay, so what do we have? We have the kinetic energy initial plus the potential, the electrostatic potential energy initial is equal to the kinetic energy final, which is equal to 0 because it's going to stop, and is plus the electrostatic potential energy final. So we have a half m, which he gave me, V initial squared plus K Q over the distance between them. So the distance between them initially is equal to 4.2 centimeters, so 0.042, and that is equal to the final initial potential energy, so Q1 Q2 divided by the distance x. So as you can see, everything is given. This is also given, it's 66, right? And so the only thing that is not given is x, so you solve that for x and problem solved. Okay? All right. Last question. What does it say? It says that, the one before the last. So he's saying that we have these two concentric conducting spheres, and he wants you to find the first thing, one of the initial one, or the inner one, has a charge 2q, and the outer one has charge, this is 2q, and this has a charge 4q. Now we've done this in the previous tutorial, so I'm not going to elaborate on this. So the first one used Gauss's law to find the electric field at this point here, okay, which is equal to 0 because that's inside a conductor, and at the electric field at this point here, which are greater than d, you just have to, it's 4 pi r squared E is equal to the net charge, which is 6q divided by epsilon, and then you can solve for E. Okay? Okay, so that's it. The next question, B, part B, he's asking you to find the net flux Okay, the net flux, and you see the answer here. The net flux is simply the charge enclosed divided by epsilon. Now he wants the net flux in the region between B and C, the region between B and C, which is here. That's what he wants the flux. Okay, well, what's the flux? The flux is defined as Q enclosed divided by epsilon. Well, what's the enclosed charge there? It's 2Q divided by epsilon. That's your solution. Okay, that's it. Now the last problem, this one here, is I was surprised. I was a little bit surprised because we've done this for the electric field and people mixed up this question. So what we have, because now we're doing the potential. So here you have an arc that carries a lambda coulomb per meter, and it spans over an angle of 135, and he wants you to find the potential, as you can see here, the potential at point B. At point B, this point here. He wants the potential here. Okay, now we know the definition of the potential is equal to K dq divided by R. Okay, now lambda is the constant one. Lambda here is constant. So if I split this arc into small dq, now I know that q is equal to lambda multiplied by s. It's the arc. So I have dq will be equal to lambda ds. And ds, of course, s is equal to r theta. S is equal to r theta. So then ds will be r d theta. So that means my dq, as we've done before, dq is nothing more than lambda r d theta. Okay? Lambda dq is lambda r d theta. If I put that in here, and this is where some of you get mixed up. So this will be the integral of lambda r d theta over r. Okay, so these guys will go, and I have a k lambda d theta. Now this time I don't have the cosine theta. Why? Because this is the potential, and the potential is a scalar quantity. It's not a vector quantity where I have to find the sine and the cosine. So this is simply from 0 to 135. D theta is equal to theta. So simply is equal to k lambda theta, and theta is from 0 to 135. And remember, if somebody will tell me, Doctor, wait, this is k, this is the potential, and the potential is proportional to r. Where did the r disappear? Well, let me show you where the r disappeared, because I think this is the question that, and I'll conclude with that. So remember what we got. We got v is equal to k lambda and then some theta initial minus theta final. Okay, but what is this guy? Lambda is equal to, q is equal to lambda multiplied by s lambda r theta. Okay, that's what q. So if I substitute for lambda, then k is equal to q over r theta. Theta is here. Here you go. K q over r, and that's your usual one, and that's it. So that's the potential at this point, and thank you very much, and see you inshallah tomorrow.